I'm Nicole Jardine. I'm the Chief Data Officer with the County Assessor's Office. I'm here with Michael and Jeannie, who will introduce themselves when they're turning to take over. And today I'm really excited to talk about machine learning explainability and how we generated 1.9 million web pages to try to explain the statistical model that produces estimates of property values. First, I want to talk about data science and transparency at the Assessor's Office. The data team at the Assessor's Office is responsible for something called the model. The model is a computer program that uses vast amounts of data to estimate current property values. This model produces estimated property values for roughly 1 million homes in Cook County. And our goals for this model are to be accurate, equitable, and transparent. We have been to SHAP before. This is from Dan Snow's second talk about that model that we use to estimate property values. There's been a lot of great work, and this model has become better and better over the years than previous models. What I'm excited to talk about today, though, is about making that model more transparent. We're here today to answer that big transparency question. How did the model assess my home? This is the question that we've been asked for 6 years since I joined the Assessor's Office. And what we're trying to develop is an exploratory tool that was recently launched to try to answer this exact question. So how did the model assess my home? We're going to do a little bit of data science 101. To estimate your home's value in a way that fairly and accurately tracks the real estate market, this statistical model relies on 2 kinds of data. The first are sales. The model needs to know what real estate transactions are like, which property sold, when it's sold, and how much. But we also need to know characteristics about that home. Larger homes tend to have higher sale prices than smaller homes. Homes on the north side of Chicago tend to have higher sale prices than homes on the south side. Models need lots of characteristic data about properties and sale data so that they can learn trends between these characteristics and sale prices. Again, the model's job is just to learn about the real estate market in these different neighborhoods and to learn patterns between the characteristics and sale prices so that it can fairly apply those patterns to predict an estimated value for a home. So the output of the model is, here's what the model thinks this property is worth. Okay, so back to this question. How did the model assess my home? I'm extremely proud of the work that the Assessor's Office has done in trying to make all of our work transparent. From day one, we have published our model documentation and every line of code on GitHub so anyone can read it. And that's great if you are a data scientist who knows how to read code. But it's maybe not very accessible for an average homeowner trying to understand how a home is valued. It's also not very specific. This RDP is really great general introductions to modeling, and it talks to a lot of the decisions that we've made, but it doesn't tell you here's how we assess your specific home. Similarly, for years, we've also been publishing data on the county's open data portal. We publish sale data, we publish property characteristics. But to use these assets, you have to know how to go on this web portal, apply filters to look at specific geographic areas, or filtering on different property class codes and who knows what those are. Again, this is a great asset for sophisticated users who understand things like APIs, but it's not great for average homeowner who just wants to know how the model assess my home. Finally, we also publish reporting dashboards containing aggregate stats about neighborhood sale trends. Again, this is really great because a lot of homeowners maybe don't know about recent real estate market trends in their area. But again, these are averages. They don't talk about your home specifically. So, for the last couple of years, we really had this dream to build something that explains how the model assesses a specific home. And we wanted to do it using the sales and the characteristics that the model relied upon most to arrive at an estimate of a home's value. So what I'm excited to share is this exploratory new tool that first we had to create some new explainable AI data science methods combined with some pretty sophisticated web dev watching, you can actually follow along online. And for those who are in person, I'll bring that on the screen. I'm going to demo this using the HomeVal house. So to follow along, you can actually do this on your phone. The tool that we're showing you today is mobile friendly as well. You go to the Assessor's website at the County Assessor on their website. Under the data tab, you select HomeVal report. And then you're going to enter this PIN number, and then the default your assessment for this county HomeVal. And I'm just going to switch over to this report. So this is one of these 1.9 million static web pages that we generated to explain the model. I'm going to zoom in here. And at the top, we explain a couple of important things to understand about this exploratory new tool. The first and foremost of which is this is an exploratory tool designed to explain a pretty sophisticated statistical model. It is not like the new prompts tool. It doesn't replace any of those already exist there. We've also built in text tooltips so that users don't have to Google things like statistical model to figure out what that means. People can click to read more about this report. For example, they can read the article that we've written to explain the algorithm here. At the top, we have, you can print the location and just a couple of size and age characteristics about the home. This is good to kind of confirm that the user is looking at the correct home that they're intending to look at. The HomeVal house is in the tree. And then we keep going and we get to the really interesting part of this report. The rest of this report is focused on an idea, which is that of the tens of thousands of sales that the statistical model uses to estimate property values, some of them are probably going to be more important to estimating the home's value than others. In this report, we're selecting 5. So we take these top 5 sales, and the first way we want to show them is we put them on a map. This is an interactive map. Users can zoom in. They can hover over each dot and click on it, and even select more to learn more, and even see photos about that.
Location data, census data. It takes the same splits all the way through the tree. The data, the feature data there is similar enough that it's the same path, and then it ends up in the same terminal leaf node and gets from this tree assigned the same value. And so this is kind of a way that we can kind of say that the model is thinking about these two homes in the same way. So when you look up your home in the HomeVal app, here's another toy model of 5 trees here. We have the terminal leaf node that your home ends up in for each tree. When we look it up on HomeVal, we compare your home's terminal leaf location for each tree to every single sale in the training data to see how many trees they share the same terminal leaf nodes. For example, for sale 1, for tree 1, both end up in the same terminal leaf node. Tree 2 they don't, tree 3 they do. And then we tally up how many trees the sale in your home share those terminal leaf nodes. And then we count it for every single sale in training data. And we rank them based on the highest number of shared terminal leaf nodes. And then we pick those 5, and those are the 5 that will show up on the HomeVal app. We think this is a very cool algorithm because with algorithms that are like linear regression, they're much more interpretable. It's much easier to kind of make statements about their structure, how they're thinking. With these more complex tree models, it's much more difficult. And so, kind of taking advantage of the structure of the tree to say something about how the model is how the model is thinking about your home and sales is very cool. There's a very small amount of information out there on some of these matching techniques that exist. There's not much building information on Question?
Yeah, I can hold it till the end though. But
Maybe,
is it better now or later?
maybe later.
Okay.
So, yes. So as you might be thinking, for every home, we compare its data to every single sale, which could be 100,000 or more. And then for all of those comparisons, we make comparisons on over 1,000 trees for each one of those. So it's can be computationally expensive. Our team has done some, particularly Gene, has done some awesome engineering work to optimize the algorithm, speed it up. We use nominal high performance Python code. This allows us to pre-compile Python functions, which gives us a big speed up. Cook County is split up into 3 triads, and each triad gets reassessed every 3 years. So we only make comparisons for homes that are up for reassessment. This is a big subset that helps us. We parallelize these comparisons on multiple quarters. So instead of just doing one comparison after another, we can run multiple of them at the same time. And we use AWS to basically use their faster and more powerful computing resources. So I will turn it over to Gene to talk more about the engineering side and how we built that.
Thanks, Michael. How is everyone feeling? Raise your hand if you're like, I'm following 100%. I could do this because I could get those slides. Okay. Raise your hand if you're like, I could see that one more time and that would be pretty helpful for me. Okay, cool. Raise the volume? Okay, great. I'll try to project. We can come back at the end of the presentation and talk more in the details, just to make sure everybody understands the algorithm. I think it's very interesting. I think it's like somewhat simple and we could get there. But we'll put a pin in it for now. The key thing is just like we're finding the sales that we think are the most similar to your home based on the structure of the model itself. Is my volume okay now? Go a little further? Okay. No, it's great. Okay, perfect. Okay, in that we can come back to it. I'm going to shift to talk about the web development side of this. So we're going to talk about how we actually took the algorithm that Michael described and turned it into the website that Nicole showed you before. As we were thinking about like how are we going to build this, some things that were on the top of our mind. We wanted it to be cheap. We wanted it to be easy to maintain. We wanted to be able to change it quickly, so simple to deploy and fast. We wanted it to look nice because everybody likes their websites to look nice. It needed to work on a phone because that's what most people use these days. It needed to be fast, so if you don't have a great internet connection, you can still see it pretty easily. We wanted it to last, so anyone who joins our office later can pick it up pretty easily and maintain it even after we're gone. And we wanted it to be simple enough to understand that you don't have to be like a trained data scientist or assessment professional. So you all will be the test of that for us at the end of tonight. If you can understand it, I think mission accomplished. So this is what we were thinking about, and I'll show you here a sketch of the architecture for the app. We'll talk about each of these in detail, but at a high level, here is what's going on under the hood. I'm going to try to explain all of these things as simple as possible, but if you haven't done web development stuff in the past, it might be a little confusing. That's okay. We can talk about things in detail later. But, so here's the way that everything is flowing. We start by computing the significant sales that Michael was talking about. So we're going to run that algorithm on AWS, on Amazon Web Services. They have a service called Batch, which is a batch compute platform. So you can rent servers, you can rent computers from Amazon, and you can run large-scale data processing jobs. So that's how we're going to compute the significant sales. We're going to save that data to Amazon's file storage service called S3. So we save it in a analysis optimized file format called Parquet. So that batch process outputs a Parquet file to Amazon S3, the file storage service. We're going to take that raw data, add it with some other contextual data that we have from our modeling process in our data lake. And we're going to produce transformed data that we can use to power the app. We do that with a tool called DBT, which is a data transformation open source tool, and Amazon Athena, which is a serverless database, an analytics-focused database. So that's like our transformation layer in the extract, transform, load pipeline, which is a common like data processing term. So we're going to take our raw data from S3, we're going to transform it with DBT and AWS Athena into a format that is closer to what the application needs. And then we're going to use a GitHub Actions workflow to actually generate the website. So GitHub Actions is a remote code execution platform that's built into GitHub. And you can run code on GitHub's machines. You can do whatever you want with it. We use it to generate the static website files, the HTML pages that you actually see. We generate one per parcel per year, which is about 1.9 million per assessment year. So the type of it happens from. We use a framework called Hugo for that, which is a static site generator. So you can give Hugo a markdown file, and it will generate an HTML file for you based on that markdown file. So we're going to take our data, we're going to turn it into markdown files, one for each parcel per year, and then we use Hugo to very quickly generate HTML pages for each parcel for each year. And then inside that GitHub Actions workflow, we'll upload those files to S3 again. And then S3, it's both where our raw data lives, and then it's also where the website lives too. And so we're going to put a content distribution network on top of the S3 bucket. That's the final layer. It's actually acting as the server that's taking requests from anyone in the world and routing it to our S3 bucket. Someone says, I want this pin in this year. The content distribution network is going to find the file for it and give them the file. So a lot of complexity here, particularly if you haven't done web development stuff, but I think like the key thing to take away is that we're just working with static files. We're doing all of our data processing up front, and then we're using this workflow to generate one static file per home per year based on that data that we've got processed. And then whenever somebody loads a page from the website, they're just getting a small static file. It's often cached too, if somebody has requested that file before, which is where this content delivery network comes in. So all of this is intended to make it very simple. It's all static files, and it's very fast too. It's serving static files, it's very cheap, it's very fast. That is like very quick overview of what's going on with the architecture. A little bit more, just like an example, maybe to sink your teeth into for each of these pieces. These are the logs that we see when we're running the significant sales algorithm on AWS Batch. You can see we're tailing logs here in no time, we're getting a timestamp, and it's telling us I'm this far along in processing. So this is like the batch processing step. It's running on a remote machine. We're watching it through the logs if we want to. Sometimes we're sleeping because we're running it overnight. But that's kind of what that component looks like, that first batch processing step. Next, after we've got the raw data, is the transformation step. This is a little window into what that looks like. The transformation step is mostly SQL. It's mostly database queries. There's two sides of that. On the DBT side, we're defining SQL queries that show like the shape of what we want our raw data to look like and how we want to join it with our other data. So we're writing a SQL query here that's saying, let's take our runs, the algorithm, and let's join it to our model values and our home characteristics and make a table that we can use to power the application. So that's what's going on here, and then DBT is going to package that up and make sure the data is transformed. On the right side here, you can see the other half of that, which is we can write SQL queries to query that data. So once we've defined what we want it to look like, we can just query everything from the table we've created. We get a nice view into the data that's easier to power that app. And so this query here, that's what the GitHub workflow is going to use. It's going to use the transformed version of the data. This is a little window into the logs for the GitHub workflow. On the right-hand side, we're seeing everything that it's doing. It's querying all of our data. it's querying more data, it's formatting it together, it's telling us how many homes it's running through at any given time. Eventually, it's going to be uploading the sites at the bottom. And then on the left-hand side, you can see that we're parallelizing it. So we're making small chunks of the county. And we're only running like 5,000 reports at a time on one machine. So that way, we get 30 machines to run all at once in GitHub Actions, and we can do 1.9 million homes in like 1 hour, basically, instead of it taking a day. So that's a little window into this is like when we're building the app itself, the static files, this is what we're looking at. This is how we can keep an eye on what's happening. And then at the end of that step, it's going to upload each of those files to an S3 bucket. And this is what that S3 bucket looks like. It's just, we've got a folder here for 2025. And then we have one HTML file for every, this is like a, we call it a PIN. It's a unique identifier for a home or a parcel, technically. And so we just have one of those for every home. And when you go and request your PIN for your year, the CloudFront Distribution Network is just going to find it in the bucket here and give it back to you, and your browser is just going to render it like that. So lots going on there, but basically what's happening is we're splitting up our batch processing. We're doing all the computation up front. We're making these static files and just storing them in cheap, simple static file storage. And then we're putting a content distribution network on top of that so that all you have to do is request the static file that you want using the search page, and it'll load pretty fast, even faster the second time. That was also a lot. We can also talk more about that in detail, but just to finish off, the reason that we went with this architecture, I think some nice things about it is it's very easy to automate. We have total design flexibility because we're just making HTML files, so we can make them look as beautiful as any web page. We're not constrained by a framework. Our response times are really fast. We're just working with static files. We pay for what we use, which can be good, but it can also be bad. People use it a lot. AWS might end up charging us a lot, so I think the downside of this approach is it could potentially cost more than other approaches. You need to have AWS, you need Amazon skills to maintain this, so that's definitely a risk that we have to consider. And also, I think the deployment stack is a little bit complicated. You maybe got a sense of that. Complexity, I think, is its own downside too. We can talk more about that. But these were sort of like the pros and the cons that we were weighing as we decided to go in this direction. And if you're interested, we can talk more about other options that we considered and how those stacked up against this one. But that is like, in a nutshell, what's going on when you actually load the website. Cool. Nicole has a last slide, and then we'll take questions.
Yeah, I want to thank you. I also want to thank Dan Snow and Claire Boyd, they developed the initial first draft of this algorithm roughly 2 years ago. Back when I first wanted to try to explain this. You can check this out online. We have the repo for this is public. Our GitHub group is listed there. The repo is HomeVal. Again, here's the URL for that web app. You can read more about the algorithm in a vignette for one of our other packages, and we'll answer questions. You can also email us at assessor.data@home.org. Thank you all so much for your attention, and we would love to take your questions. You have a first question.
I did.
Yeah.
Thank you. Thank you for the presentation. The question is actually, in the early part of your presentation, I asked the question, why did you choose the 5 when you use your top sales? And I would ask you to define what top means. And in your presentation, you said the most significant sales. I would ask you to do the same thing. What I hear as a homeowner, we're leaning more towards more expensive homes and valuing the collective body of homes that will pay taxes against people who are selling their homes versus those who are super staying. So I could be wrong, so I'm looking for the data from the two of you and what those 2 terms mean.
Cool. I'll take that first part for Wi-Fi sales. Yeah. Wi-Fi. The model uses tens, hundreds of thousands of sales. How do we get to this number 5, right? In the development of this algorithm, we did a lot of analysis to try to figure out, is this exploratory algorithm doing what we think it is? returning sales that are predictive and explaining what the model is producing as an output estimate for this one. And we analyze things like if we look at the sale prices of the first two, first three, first five, first 20 homes that this algorithm is returning, how many of those seems to basically get out of the model is doing. And we found it kind of had reached this asymptote at around 5-ish maybe. So we went with that. It could have been 10, could have been 20, even 2 that got up to, right? So for this one, 5. We could have made other design decisions for the app. For example, only showing some that have like a certain score, but for this, we went with 5.
I just want to put one question to you. What I'm asking is, why did you choose the top 5? So when your value is greater than normal, defining the top.
Sorry, you're right. Thank you for clarifying. We think these are top as in the sales that are most similar to your home, not the top price.
And then how do you define most significant factors?
Yeah, this is the 30-second menu. There are 2 ways to do this, right? There's one way to do it, which is, let's just draw a net around this house and pick sales that are maybe sort of similar. And that can work if you are just looking for sales that are similar. But the goal here is to actually give transparency into what the model is doing. So what we did is try to build an algorithm that actually analyzes that tree structure. So earlier Mike was explaining how the model works. The model learns things like bigger homes have this much value associated with it, smaller homes have this much value. And so this algorithm is trying to reverse engineer the model to get at the sales that are just most like the real home. Do you want to unpack it or do you want something?
Maybe. I'll just add that I think like the top versus significant. Not actually, we're not trying to describe a distinction there. In all cases, I think we're just trying to put a word on the algorithm that Michael described. In all cases, what's happening is the algorithm that Michael described, and I think top sales, significant sales, it's all just trying to figure out like how do we summarize what the algorithm is doing. So there's no difference when we say top sales, significant sales. We're just trying to say like the sales that were linked to the highest according to the score.
But we don't do any sort of price-based selection. It's purely like of this algorithm.
You should choose.
Yeah. So you generate all of the static HTML files using GitHub Actions in parallel. How is that orchestrated?
How is it orchestrated? Like how are we running it?
Yeah.
We run it on demand because there's one model per year, and we're explaining that year's model. Basically, it's just like once per year we trigger it through the actions.
It's all just deployed via GitHub Actions.
That's all, yeah. And then that, that's we get the GitHub workflow pushes to S3, and that's the we have run it many more times than one in the process of developing it. But the goal is like once per year we'll run it with the next one. If we need to change something, if there's a bug or we want to like tweak the language when we're describing it, then we would go and ensure that we do it. But there's no like automated introduction. How long does it take? It took about an hour. So the calculation of the sales, the like top 5 most significant sales, that takes longer, and that happens once too. Each like deployment of the web pages takes about an hour. Lots of questions. This is great.
My question is that algorithm is that tree model and not the linear model, and then how will that work? Do you see like next steps to how we can do our generated chatbot or something like that? But if you're using that algorithm, then how would you use that algorithm?
Great question. This is pretty exploratory. One of the does this actually provide insight into how the model estimated on value? And is it giving more insight than confusion? We wouldn't want to build like a chatbot on something that is not actually helpful for companies. So what we like about this algorithm is that we produce the top 5 most important sales, and that's it. It's not like rethinking, for example. These are static things. So yeah, we have to think about that a little more. But I don't know if we've ever deployed it.
So could you use this roles on to
I got a question. I got a question from the live stream also. Too.
Yeah, let's take a question from live stream. I think we can do about 5 or 6 now. So let's do that one first.
Okay, from the live stream, Sean, who describes themselves as a CCAO advocate or superfan, says, "Do you have any intuition about the net effect of new developments on surrounding property values?" And I guess the second part is it feasible for an individual to do their own analysis using your model to determine how a new development would impact the property values? So like, what do you think about new developments? And then can you use it, do it yourself to say if there's something new?
Yeah, I think that's a really interesting question. I think that the most direct link there would be that, as Nicole was saying, one feature in the model is proximity to new construction, which is sort of like trying to get at like what's the intensity of the development in this neighborhood. And so, like one new building would change that. I think I don't have an intuition necessarily for like how that would change your value. I think it's up to the model to decide in the learning process. I think that like probably what a lot of people might, the like common wisdom about new development is like the new development is going to raise the property values because it's going to be expensive, and so my home's going to be more expensive. I looked at it rigorously. I'm not totally convinced by that, if that's what Sean's getting at. I think one thing to keep in mind is that like the age of your property is consistently a very important predictor for your value. And so like a brand new construction is going to be very different from your home, unless you own brand new construction. If you also own brand new construction, then the sale price of that building is probably going to track pretty closely to your value. But if you don't, then it's up to the model to decide basically what's the effect of age in this. And those are like 2 very different things. That makes sense? What did you ask?
Yeah, basically, if you own a 100-year-old home and there's a new development and it's a year old and it sells for $1 million, age is a really big determinant in property value, right? So because the model uses these characteristics like age to discover price differences, the model will learn if in your neighborhood, year-old homes sell for similar prices than 100-year-old homes. Seems unlikely, but it could happen. So the model will basically pick up on statistical patterns between age and price.
Let's go like 1, 2, 3, 4, 5. One person. Yeah, perfect.
Oh, so I have a question. You said if the model compares off similar homes. So my question is, how do you tell if the data that's related to the model's accuracy? I've seen so many homes that are not factually correct to what's actually inside the home. Like, let's say this has 3 bathrooms, it's just 1 bathroom. It actually has more or less bathrooms. How do you actually factor in that for the correct price? Because a lot of people haven't been inspecting the homes inside the home.
Yeah, our office inherited a set of property characteristics that sometimes up to date and sometimes are not. It is important that we use the property characteristics at the time of the sale so that the exact property characteristics when it's sold are used to train the model. Here's the problem. Let's imagine 800 square foot house in a neighborhood where maybe the prices tend to range from 400 to 600. Sometimes in our data we might see something like $1 million sale price that match to that 800 square foot home. And that would be what the property sold for, but what happens sometimes if you look at this, this home is no longer 800 square feet, and maybe for 5 years, it was redeveloped 5 years ago, it's now this 2,000 square foot, new building, right? So that presents a data quality issue. We don't want that sale to train the model, because then the model is going to learn, 800 square foot homes in this neighborhood sell for really well, and we don't want that sale to be used for property values. So we actually have a separate pipeline to try to identify these extreme values before they're used in the model. Very much.
Yeah, this is really interesting and informative. I was wondering about what does usability look like? So you even at the level of the tooltips, I think you walked us through some of the technical aspects, and then you were thinking about how people are interacting with it. How are you getting a sense of sort of the curricular path that folks are going to need just to be able to kind of follow along?
This is so new that we're kind of still in the early evaluation stages. We would love to hear feedback from you all. We've started to look at use metrics, but I think they will come through when we talk to people and see what is using.
We're not tracking interaction automatically very closely, so we're not tracking where people are clicking, which is I think how Facebook would be figuring out the answers to this question. I think it's going to be sitting down with the taxpayers, watching the research. We've done a little bit of that. I think that's the next step for us is doing that in the area this year.
That makes sense. I got some ideas. I'll find out after.
Yeah, please do. That sounds great.
Cool. Let's go through now. So let's go to Jacob.
Hi, this has been super cool. Correct me if I'm wrong, but it looks like you have what's ultimately a black box model, and you're adding in the interpretability post hoc. Has your office had an opportunity to look into so-called glass box models? Explainable boosting machines where the interpretability is built in from the beginning. It doesn't have to be, added at the end.
We should chat after and chat about this model. I think we're very interested in that. I think that I have not personally evaluated glass box models yet, but always interested.
Yeah. One of the reasons that we went with like GBM in administrative inclusive tree model is that tree models tend to be more explainable than, say, neural nets. And there are explainability tools like something called SHAP values around them. But when we started to do some evaluation of do SHAP values help people understand the model, it turned out that those weren't helpful. So that's why we tried to think about a new explainability method.
Yeah. Agree about SHAP values and EPMs are treatments. So,
Yeah, let's try that.
Cool. We're gonna do 2 or 3 more down the line. So 1, 2, and then this. 3. Yeah. Max.
Yeah.
Max.
When you're talking about a similar property, does your models and your analysis mean like you're showing a house that was in a movie that's very distinct and very different? So we're sure there's a whole bunch of valuation judgments that people use in sure to sell homes that come differently in those second time. Does the model work geographically from place to place when those decisions vary in people's heads?
Basically, does the model take different geographies into account?
Different geographies, but the underlying bundle of reasons that people value property differently in those geographies.
That's the answer that is that if there is something within a geography that the model learns is differentiating properties there, then it has statistical information to learn that property values differ based on this characteristic even within that geography. Sometimes that might
think I'm doing a bad job asking the question. So like if the models, the training data that the model uses to make its splits into trees and stuff like that, is that based on Cook County-wide information, or is it based on an individual neighborhood?
But we use sales from across the county to in the model. So and this is really helpful for the model in the case of outlier properties. So like the home house, one of the things you mentioned, there might not be many sales of really big mansions in that neighborhood or within this area. So the model is able to leverage sales from across the county to try to learn these statistical trends. Again, that's important if you have a home that is kind of unique in its block, then other sales on your block are not going to be comparable to your home. So for that reason, yes, the model is allowed to search countywide for these sales. We don't tell it to like constrain itself to certain areas.
Okay, so last few questions. This gentleman and then over here, and then we're going to switch it.
Okay, so to piggyback on what you just said, so as a property owner, this is my battle that I have with the assessors all the time. I have them all on like, a little spreadsheet of all the people. So when I look for comparisons, so they came up with their little data on my evaluation of my house. Okay, great. I'm going to come up with my own comparison based on your software that you provide, right? So now this is what's really ridiculous, I think. So they say, okay, when you're looking for comparisons, we restrict you to be in a certain demographic area, not citywide, right? In a small little box. This is where we assess property, similar to yours. When you're looking for comparisons, I did it within that parameter where it's coded, right? There's code. They rejected it. Oh, it's too far. It has to be only 1 or 2 blocks from your house. I said, what are you talking about? As long as it's in that same boundaries that you limit properties that are like properties, then I should be able to go at the very edge of that box on all 4 corners and pick houses that are similar to mine, not proximity to where my house is located. Right? So there could be a house at exact same demographics, statistically, could be at the very edge of the boundaries, and that's what they should be looking at, the data, right? So the age, the size, all these things, not where it's physically located. Right? If it's within that little box where they put every, I don't know, I forgot the term, like code, or, so it's a township is one demographic. So look at township. Then they even narrow it down to only a certain few blocks, right? And you have to be within that little tight constraints to be considered valuable comparison. So it's ridiculous. I should be able to look all over, but even within that box, right? In that box, it should be that whole criteria, not 1 or 2 blocks from my house. Because they say, oh, it's more than 6 blocks. We're not going to consider that. Oh, it's more than 8 blocks. So, you know, I don't know if we're going to reevaluate that and now give it a broader search, because based on what you just said in selling property, right, it's not in that box, right? It's all depending on where the house is. Just like you just mentioned, a mansion may not be plentiful throughout the whole county, because maybe there's only one mansion that sold in the past 5 years because they don't sell it. So where do you do it? You have to do a broader search. When you do a broader search, how come the county is allowed to do a broader search to come up with evaluations of a house? But the homeowner, when they're doing comparisons, they can't use that same type of data. And so I think it should be fair on both sides. If you're able to do a broad search, then we should be able to do that.
To the best of my knowledge, you can submit anything you want with your PLM analyst to look at things. I'm curious though, you don't think that proximity has a big effect for home?
Because, like I said, okay, so if it's same size,
right? So think about when you evaluated the house to begin with, right? So you're looking at sales. So where I live, maybe no one sold anything because it's not a transient neighborhood, right? They don't want to make a quick buck and sell it, right? They want to be stable, they don't sell it. So if there's no one selling any houses within a certain demographic area, then what do? The assessor has to go further out to find comparisons, right? So maybe there's none, 4 or 5 blocks, 10 blocks. No one's selling anything. So what do? They have to have to come up with a number to evaluate my house. So they have to do a broader search to find where are these people selling these houses. So that house could be super far away because no one in the immediate area is selling. Now, so you're doing that, right? You're doing broader searches to find a house that's selling, but you don't let us do the same criteria in getting comparisons, right? You want me to be pigeonholed into one little section.
You can chat more, but that's to my knowledge, you can submit whatever you want.
Yeah, but they reject them, right? Because I speak with the analysts. Because as far as I have a right when I contest it, they ask you, do you want to challenge it? Yes. Do you want to speak with the analyst? Yes.
And the other thing I was also going to mention is, I think it's important to distinguish the more common kind of property appeal. And again, I should say, we are not the residential analysts. We do not make appeal decisions. The more common type of appeal is called a uniformity appeal. This is the complaints that my home is not assessed similarly to homes like mine. This is different. This is about sales data. So I think what you're talking about is the uniformity research, and I'd be happy to talk a little bit more later about the difference between what that is and what this is, which is it's not comparing uniformity. It's like purely looking at sales data.
Yeah, but that sales could be outside of my neighborhood, right? Because no one sold anything in my neighborhood, so they have to get those sales statistics outside of the neighborhood.
Apologize, I think we might have to move on to our last question. I'm sorry about that.
Yeah,
It's okay.
so time for one quick last question.
This could be
Maybe
anticlimactic now. I'm kind of curious, like when you came up with the similarity algorithm, if that's sort of the best way to think about it, when you compared it to other methods like SHAP or Lime or even just like clustering, what metric did you use to kind of evaluate that? Like
Great question. We first tried to use SHAPs just internally to try to explain kind of our property value and how the model came up with this. The SHAP values are produced by the model trainability tool. It shows for each characteristic the value that the model added for example, square footage. Oh, it's 150 square feet. This adds $3,000 to the home. It's in this school district. This adds this. It is a smaller, fewer bedroom, so it subtracts 2,000. So these SHAP values are output by the model of sustainability of AI tool. And what we found is they're really confusing because they can be negative numbers. So people would see a SHAP value of, 2 bedrooms minus 6K, I think it's somewhere. And they would think that, so I have bedrooms and it's subtracting from my home's value. The other confusion is that people would think that if it was, say, if our model had it at 4 bedrooms and a SHAP value of 4,000, and they say, it's actually 3 bedrooms, it shouldn't be 3,000. Bedrooms actually don't have a huge impact for most of the properties, but we found that it introduced a little more confusion than it helped. That said, I don't know, I think maybe we kind of abandoned SHAP values too early. I think there might be other ways we could use them to explain the model. Does that answer your question? We kind of tried SHAP first, and then people were kind of like, okay, so it says 6K, but where did the 6K come from? So we thought, okay, maybe we can try an exploratory new tool to find the sales that the model used to come up with that 6K.
Okay, let's give a big round of applause to our panelists.